the camera again, because the camera, there's a law that says if cameras can record for more than half an hour, you have to pay tax on them as video cameras. So even though technically, physically, like the camera could record for more than half an hour, because I stuck like a really huge video memory card in it, but then in the EU you would have to pay extra tax on it, so the software stops it recording after half an hour. And yes, you can hack it, but then it voids the warranty. And yeah, I don't really care about the warranty, but I also don't want to hack my like, there should be a nice way to do this. Also, this way it breaks it up into nice thirds. Okay, so let's talk about three-colorability. So this, it gets a little bit complicated. So nobody's ever found an algorithm for three-colorability. Now I want to talk about I told you, oh, I have to start this again. Reset, start. Okay. Now, I told you planar four-colorability is easy. You just say yes. But general four-colorability, so if the graph isn't planar, you don't always say yes. For example, if I give you a 5-clique, then the answer is no. So I want you to see that if you could do, so this will be the first time you sort of see a real reduction, not a real reduction, but if you could do four-colorability, then you could do not planar four-colorability, then you could do planar or not planar three-colorability. So notice that if you can do planar three-colorability, it's not immediately obvious that you can do general three-colorability. But if you can do general three-colorability, planar three-colorability is a special case. Somebody gives you a planar graph and says, is this graph three-colorable? If you have an algorithm that works for three-coloring any graph that can be, then you don't care that it's planar. And it will turn out later in the course that if you have an algorithm for planar three-colorability, you can use it to get an algorithm for general three-colorability. So this is getting a little bit sneaky. Okay, so did I do this in the last class? No. So imagine that you have this graph, G, and you want to know whether G is three-colorable. Okay, but you don't, but you have a magic box. But it doesn't, that will tell you about colorability of graphs, but it doesn't tell you about three-colorability. It only tells you about four-colorability. Okay? But general four-colorability. It doesn't have to be planar four-colorability. Then what you can do is you take G and you create this new vertex V, and you connect it to everything in G. Okay? So now this whole thing, you're going to call this G prime. So observe that G prime is four-colorable if and only if, which I'm going to write IFF because I'm lazy, G is three-colorable. Why? Because if G prime is four-colorable, then just take V away, and G has to have been, the remaining part of G is three-colored. Because if there were an edge which had two endpoints the same color, then there would be that same edge with two endpoints the same color in G prime, right? So if G prime is four-colorable, then G is three-colorable. Now suppose that G is three-colorable. Then G, this is all three-colored, and you just use the extra color for V. Okay? So this is sort of a super simple reduction. So note that this doesn't this requires four-colorability, not planar four-colorability, because you can have the graph, and if you connect V to all the vertices, that doesn't maintain planarity. Okay, even if G is planar, G prime may not be planar. Okay, so for example, if you take is a K33 three colorable? Yeah, I think a K33 is three color. I think a K33 is yeah, it's bipartite, so it's two colorable. So if I give you a K33, which is well, a K33 is right. If I give you a K23, right? So this is planar. So this is connected to here, and this is connected to here. Right? So these are two bipartitions, and it's a K23. So everything on this side is connected to everything on this side, and everything on this side is connected to everything on this side. Now, if I add another vertex, then I can't, then this becomes, and I connect it to everything else, then this becomes not planar. Okay, I think, I just made it. I should check that later. Okay, so you see how this is starting to get a little bit. Should I use, let's vote, should I open the new markers? So you can see that this is starting to get a little bit complicated. You have one colorability, two colorability, you have planar, four call, and then planar 5 call, and so on and so on. So as many of these as you want, and this is also, you have like Eulerian cycle. And then over here, so this is sort of the clink side, and over here on the boom side, we have planar 3 colorability. Can you read this? Yes, we have polynomial time. Now we actually don't know if they're polynomial time algorithms for what I'm listing here. We can't prove there aren't, but we've never found any. So there's planar 3 colorability, there's 3 colorability. People are saying yes, they can read that. There's 4 colorability. There's 5 colorability. Why? So if we know that, so we know that if planar 3 colorability is hard, 3 colorability is hard. If 3 colorability is hard, I just showed you that 4 colorability has to be hard. So this is stuff this is clink, and this is boom, to use the technical terms. Okay, so I just showed you the 3 colorabilities. If we can solve 4 colorability, then we can solve 3 colorability. The same argument says that if we can solve 5 colorability, then we can solve 4 colorability. Yeah, let's not get into the P and NP stuff. That's a bit much for the second lecture. Let's stick with clink and boom. That's nice and non-threatening. Now, also, what we have is a Hamiltonian cycle. Now, the cool thing is, now notice that if you also get, if you wanted to, you could solve, if you had a magic box that solved 3 colorability, You could use it to solve two-colorability, right? You would just do the same thing. You'd add on another vertex. This would seem not to be very helpful because we know how to solve this and we don't know how to solve this. So it doesn't help to reduce stuff we can solve to stuff we can't solve. But if you had the magic box, you could definitely do that reduction. So I'm going to say planar three-colorability is, if you can solve this, you can solve this, right? So I'm drawing the arrows this way because I'm taking an instance of this and I'm turning it into into an instance of this, right? I had G, which is an instance of three-colorability, and I turn it into an instance of four-colorability by adding another vertex. We don't know if clink equals bool. Well, so some problems we know are hard. We just don't know if NP-complete problems are hard. So this turns into this. Later in the course, what we're going to see is that actually you can also, you can go backwards, but not directly. What we're going to see is that there's this problem called SAT, and then there's a problem called 3-SAT. And SAT reduces to 3-SAT, and 3-SAT reduces to 3-colorability, and also 3-colorability reduces to planar 3-colorability, and 5-colorability, blah, blah, blah. And also Hamiltonian path reduces to SAT, and 3-SAT reduces to Hamiltonian path, and 5-colorability and whatever reduces to SAT. And so you get a cycle, so all of these things are equivalent. So all of these reductions work in polynomial time. SAT is the problem of determining whether a propositional formula, a Boolean formula, is satisfiable. That's for like the last part of the course. I'm sort of bringing this in. So what I should have done is, draw those. So these blue lines so planar 4-colorability, if you can solve 4-colorability, you can clearly solve planar 4-colorability. If you can solve 5-colorability, you can clearly solve. Okay, so this kind of, these blue lines you can figure out. Notice that it would be weird. We would have found a solution to all of these if we could draw an arrow from anybody on this side to anybody on this side. So what you don't know, what is not easy are the red arrows, which are. This arrow is pretty easy, actually. It's just something you don't know yet. Okay, so those red arrows are reductions which are not obvious. The blue arrows are fairly obvious. The blue arrows you should understand by now. Okay, so let's get in so that we can actually talk about the divide and conquer part, which is what you're going to use for the homework. Yeah. So this is like if you've done Boolean, you've done propositional formulas, right? So it's not, you can think about like, how would you write a formula that says, which variables would you use, and how would you write the formula that says a graph is not 3-colorable, or that says a graph is 3-colorable? You'd have to like write down these variables and say, okay, then each vertex must have one of these 3 colors, and no edge has 2 endpoints of the same color. So if this is red, then this is not red. If this is blue, so it's not actually that hard. Okay. So this is the diagram, right? Divide and conquer. So let's talk about, so let's talk about three coloring Nova Scotia. So this is how I get this reputation for brutality. These reductions are all working in polynomial time. Reductions don't actually, all the reductions you're going to meet in everyday life are going to work in polynomial time. You can still consider reductions that don't work in polynomial time. That's sort of now the new style for these things called fine-grained complexity. Okay. We may get to that in this course if. Okay, but for right now, just assume most reductions, like general everyday reductions, work in polynomial time. Okay, so I was saying this is how I get this reputation, because last year I taught people that three colorability is it's hard. We don't have a polynomial time algorithm even to tell whether a planar graph is three colorable or not. So to tell if there are 0 three colorings or 1 or more three colorings, we don't even know how to do that quickly. And then as a homework assignment, I said, okay, now here's the planar graph corresponding to the map of the counties of Nova Scotia. Count the three colorings. Tell me actually how many there are. Told this dividing coloring problem. Yeah, so now I'm going to tell you, why am I doing this only on planar graphs? So planar graphs have this nice property that they have something called small separators. So it means that if you have a graph on n vertices, then you can choose a small number of vertices. So what is a small number? A small number is, I'm just going to make sure this is recording. Yeah. A small number is, I think it's about 2 root n. Right? So if you have n vertices, you have about 2 root n. You can take about 2 root n vertices away, and this splits the graph into at least 2 pieces, and the pieces are not very big. Okay, so I think it's if it's 2 root n, the remaining pieces are not more than, I think, 2/3 the size, 2/3 n. Okay, so and then you can recurse, because if you take stuff away from a planar graph, it's still planar. So the idea is you can take a planar graph, you can take the separator out, and it splits it up. Now, you can't do that with a general graph. Why? Because if you consider a clique, well, you take vertices away. Until you've taken them all away, you haven't split up the graph. Everything left is still connected to each other. So why are separators useful? So we're gonna this divide and conquer, right? So this is let's look at the map of yeah. So I can share my screen. Everybody is happy? Good. Ah, I lost some people. I had 61 participants, and I'm down to 59. Okay. So let's go to this. Right. So here is a map of Nova Scotia. Can everybody see my screen? Now I have to switch. I have to make this. Yes, good. Okay, so here now. Okay, so here Nova Scotia is 3 colorable. I'm not actually totally sure about that. I'm just assuming like Pictou, Halifax, Colchester, and Guysborough meet at a point. Same with Yarmouth, Shelburne, and Queens. And Digby. I mean, Digby and Queens seem to meet at a line, but I haven't actually checked, but it looks like that's a point. Okay, so how would you count the 3 colorings of Nova Scotia? So it's not that hard to find a three coloring, to determine that it is three colorable, right? Like you would just mess around and it's fairly easy to find one. But now I'm asking you to count the three colorings. So okay, so now I'm gonna share my whole screen. Okay. And I'm going to nice quadrant reader. Da, 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 da. Okay. So if you brute force the solution, right? So this is not a nice way to do something. Oh, chat. What's going on in the chat? I don't program much, so it's okay, but yes, but you can see, like, nobody has a problem understanding this, right? Like, you can see what I'm doing, and if I said, could you recreate this? If I shut this down, could you rewrite this? And someone needs I said I don't code. Okay, so this is not how you do this. So you can see what I'm doing is just running through these things in alphabetical order, and then when I assigned all of the counties a color, then I check the adjacencies, and I'm being lazy. I'm only checking the adjacencies I'm checking each edge with only one endpoint. Yes, I agree, it's ugly. So then, like, if you actually want to see this work, wait, I have to, okay, I go to desktop. And I think if I enter CMD, so then I can, oh wait, where did that go? So this is, so like, if I hit this, if I hit enter, wait, this should work. Yes. Okay, there are 1,944 three colorings in Nova Scotia. So I think you notice it actually took like a few seconds. Now actually, if I do that again, it's faster. So apparently it needs some sort of setup. But it takes, like, you can blink, right? You can notice that it's not instantaneous. So how many possibilities is it? That's actually running through every possible three color, potentially valid three coloring. So it's running through 3 to the 18 possibilities. Now, but if we look at the map of Nova Scotia, why would you do that, right? Because as far as I can tell, Cape Breton Island is not connected. Now I know there's a highway, but ignoring the highway, Cape Breton Island is an island. It's not connected to the mainland. So however many ways you can color Cape Breton Island, for every way you can color Cape Breton Island, and every way you can, so if you know the number of ways you can color Cape Breton Island, and you know the number of ways that you can color the mainland, then the colorings don't sort of interfere with each other. So how do you get the number of ways to color the whole province? You just multiply, right? Because if there are, I don't know, X ways to color Cape Breton Island and Y ways to color the mainland, for each of the X ways to color Cape Breton Island, there are Y ways to color the mainland, so it's X times Y, right? Okay, so that gets you down to only checking 3 to the 4 plus 3 to the 12. But 3 to the 12 is still, if you were doing this manually, it would be annoying. So let's use this separator theorem. We know since the mainland is still the graph of the mainland is a planar graph, we can find a small number of vertices such that when we remove them, it disconnects the rest of the vertices in the mainland. So basically we're going to find some vertices whose removal makes 2 islands, or at least 2 islands. Neither of these islands is going to be too big. So for example, what if we choose Hants and Lunenburg? Right? So if we remove Hants and Lunenburg, then you get Kings, Annapolis, Digby, Yarmouth, Shelburne, and Queens. Actually, I think on the midterm last year, no, not on the midterm because that was take home, but on something last year, I put a question of name the counties of Nova Scotia because I'd made people do this and I figured, oh, well, you might as, like, you learn some geography. And so it splits into the South Mainland and then into Cumberland, Colchester, Halifax, Pictou, Antigonish, and Guysborough. I have since forgotten all the geography. I've been in Halifax for a year. I haven't been more than a 2-hour bike ride away. So you could keep doing this, for example. You could do it another level and say, oh, well, to count the number of ways to color the North Mainland, I could split it, I could remove Pictou and Halifax, and then I'm just counting the number of ways to color Colchester and Cumberland, and the number of ways to color Antigonish and Guysborough. So now the thing is, for each way to color the separator, you consider the ways to color the connected components that are made when you remove the separator. Right? So let's see this in some code. Okay. And then we're just going to restart the camera.